Right. Welcome you once again in my YouTube channel. This is Mr. Hyper taking you through the chemical kinetics, and this is the work that we are going to look at, specifically covering the activation energy and the activated complex. Now, there are theories that follow or that are followed by the chemical reactions, and those are collision theory and transition state theory, or the activated complex theory. So when we are talking about the activated complex and the activation energy, for you look at this one all coming about as a result of the nature of molecular collisions, right? So in this case, we shall consider maybe a point before we look at how the activated complex come about. You're going to look at maybe like a molecule AB plus X to form A plus BX. Now, when AB and X are far away from each other, they have some energy, but as X approaches AB with sufficient energy, its electrons begin to overlap with those of AB, so that some bonding between B and X also starts or begins to form. And at the same time, AB bond becomes longer and weaker, all right? And as the BX bond becomes stronger and AB becomes weaker, an activated complex or transition state is formed. What am I trying to mean? You have AB is far away from X, all right? So they have some energy with them. Now, when X approaches AB, all right, with some sufficient energy, electrons begin to overlap, like electrons of X begin to overlap with those of AB. So some bonding between BX, because it is near B, between B and X starts to form. At the same time, AB bond becomes longer and weaker, right? So as BX bond is forming, because as they are overlapping, B is forming a bond with X, but it means that the AB bond is becoming weaker as this one becomes stronger. Now, as this BX bond becomes stronger and as this one becomes weaker, all right, we form what we call an activated complex or a transition state. In other words, when I have AB plus X, I'll form an activated complex represented like this. And this one takes place slow, then after which I will have A plus BX. And this one, this one happening, all these changes happening, we are going to be looking at the reaction coordinates, or we are going to look at the potential energy diagrams that show these changes. So in other words, interpret it like as X approaches AB, AB becomes weaker and AB forms a bond with X, leading to a formation of an activated complex or the transition state. Now, the background of all this, right? The background of all this is going to be covered under hydrolysis of alkyl halides, since they're in different classes. So we are going to look at the hydrolysis of those alkyl halides. More so, we need to know what activation energy stands for. Activation energy is that minimum amount of energy which the reactants must possess before they react to form products. Minimum amount of energy which the reactants must possess before they form products. Then when we say activated complex, all right, we shall meet the word activated complex. And as I defined it in the other video, activated complex is that unstable intermediate in which bonds of the reactant molecules are partially breaking. Bonds here are partially breaking, while the new bonds of the product are partially forming. So we form, like these bonds in the reactants break, we form this unstable substance, and then bonds form the product. So when I say it is unstable intermediate, look at it like this. This is the unstable intermediate I'm talking about, in which bonds of the reactants are breaking partially, while the new bonds of the product are forming still partially. That is what we call unstable complex. Then we've got what we call a transition state, because we are going to also meet transition states at some point. So a transition state, when we say transition state, as we shall see from the diagram, that is the maximum potential energy during which a chemical reaction, okay, or one can say transition state, I can define it as the maximum potential energy during a chemical reaction in which a substance present at the site, at the state, or at that state can now form products of that reaction or can give back the reactant. So what I'm trying to mean, this is the activated complex, but this is the activated complex has been formed at the transition state, meanwhile, or let me say, this is the activated complex, but this activated complex at transition state level here, still activated complex are formed at transition state, of which at this state, this unstable substance, the substance present at that very state can form products or can go back to reactants. So if I say transition state is a state of maximum potential energy during a chemical reaction in which the substance present at that state can now form the products of the reaction or can give back the reactants. Now, I'm going to take you through the theory of, because here we are going to apply the idea of organic chemistry. We're going to apply the idea of organic chemistry, and we're going to look at the hydrolysis. Okay, we are going to look at generally the hydrolysis of alkynes. Those are the ones that are going to come up with that are going to get us those energy level diagrams. Now, chemical kinetics is going to be used in this case to determine a mechanism of a reaction. So let's say determination of a mechanism of a reaction. You shouldn't forget that when we say reaction mechanism, we are meaning that detailed step-by-step description of the pathways followed by the reactant in forming the products, right? So it specifies all the intermediate stages and all the intermediate species that are formed, all right? So basically, when we are talking about this, simply look at it, we are looking at stepwise description. So all the intermediates formed, we shall be looking at the stages at which they are formed. So for example, the first mechanisms we are going to determine is the hydrolysis, right? Hydrolysis of alkynes. And to take you back now for simple organic chemistry, hydrolysis of alkynes is a nucleophilic substitution reaction, whereby nucleophilic substitution reaction is the type of reaction where a halogen atom is replaced by an atom or a group of atoms, which is electron rich, or what we call a nucleophile. So the alkynes are able to undergo this type of reaction because the carbon halogen bond, right? The carbon halogen bond is polar. What am I trying to mean? If this is my alkyl halide, this is my halide, so the carbon halide bond is polar, and being polar, it means that it is weak, and that is brought about by the differences in electronegativities of carbon and the halogen. So what happens is that the halogen atom being more electropositive, more electronegative, it acquires, or because by saying electronegativity, I'm looking at the tendency to pull electrons what is soft. So X this halogen being more electronegative, it attracts bonding electrons towards itself, all right? And as it attracts bonding electrons towards itself, it acquires a partial negative charge, while carbon acquires a partial positive charge. So when a hydroxide ion, which is like a nucleophile, comes to attack the positive carbon center, it will do so as this halide is, rather as this halogen goes away. All right, so polar bonds are usually weak simply because the electrons are not equally distributed, meaning the electrons between the carbon and the halogen are not equally distributed. All right, so the electron-rich species of the nucleophile attack the electropositive carbon as the halogen breaks off. So we are going to look at the mechanism, or we are going to look at the reaction paths this reaction goes through, and then we draw some energy level diagrams and have some simple description. So basically, I'm going to begin with let me call it kinetics of hydrolysis of haloalkanes or alkyl halides. Now, basically here we are going to look at the effect of the structure of the haloalkane, okay, which pronounces the effect upon the mechanism of the substitution. I want you to realize that the alkyl groups, you can call them haloalkanes or alkyl halides, meaning we are looking at the alkyl groups. But don't forget that the alkyl groups are electron pushing, and thus have got positive inductive effect. All right. The greater the number of alkyl halides attached to the carbon carrying halogen atom, the greater will be the polarity, and hence the greater the reactivity of that haloalkane. For example, primary haloalkanes undergo reactions by SN2O substitution by molecular, while tertiary alkanes, they undergo reaction by SN1O, what we call substitution nucleophilic unimolecular, whereas secondary alkanes undergo reactions by either SN1 or SN2, depending on the structure of that haloalkane. Now, what I'm trying to explain to you is that since we are talking about alkyl groups, one may need to know alkyl halides. Alkyl halides are those compounds that have gotten the halogen as their functional group. So they are categorized into three. We have primary alkyl halides, we have secondary alkyl halides, and we've got tertiary alkyl halides. When I say primary alkyl halide, I mean that alkyl halide where we have one alkyl group attached to the carbon carrying a functional group, which is a halogen. When I say secondary, those are the one. For example, for primary, if I say CH3, CH2, Cl, this is a primary alkyl halide simply because it is having one alkyl group attached to the carbon carrying functional group, which is the chlorine. But when I say CH3, Cl, maybe CH3. This is secondary because it has two alkyl groups, the methyl groups attached to the carbon carrying functional group. But when I say CH3, CH3, then maybe Cl, this is tertiary because it has gotten three alkyl groups attached to the carbon bearing a functional group. So we were saying that the greater the number of the alkyl groups attached, the greater will be the polarity, and hence the greater the reactivity of that alkyl halide. Now, we are going to begin with alkyne hydrolysis of the primary alkyl halides. Let's begin with alkaline hydrolysis. Of primary alkyl halide. Now, for this case, the kinetic studies have shown that the rate of alkyne hydrolysis of primary of primary alkyl halides is dependent upon the concentration of both the haloalkane and the hydroxide ions. For example, if my haloalkane is Rx plus OH, okay, we shall have R OH plus X. We form alcohols, right? So we are saying that the rate of reaction is dependent. The rate of reaction is dependent, first write the rate constant. So it's dependent on the concentration of both the alkyl and the hydroxide ion. So it is dependent on that, and then the OH. Now, of course, where K is the rate constant, this is the concentration of alkyl halide, this is the concentration of hydroxide. Now, this reaction is first order with respect to each of the participant or the participating species, whereby this is one, this is one. So the order of reaction with respect to alkyl halide is 1. The order of reaction with respect to hydroxide is also 1. And the overall order is 2 because you get 1 plus 1. What does it mean? So this is second order kinetics, meaning that both reactants must be involved in the rate determining step or in the transition state. For this reaction, both the reactants must be involved in the rate determining step. So the reaction mechanism can be summarized as, for example, I'll consider my primary alkyl halide. All right. I'll consider my R CH2X. All right, reacting with OH. So if my reaction is like this, it means that this one I've already told you that it is partially positive and this is partially negative. So when I bring my OH, I'm going to attack the positive carbon center, and this one goes off. So in this case, we shall form an intermediate, and this is what the state which we define as the transition state. So CH2, here we shall have R, and then here we shall have X. From which here you can form your final product as R CH2 OH plus X. You need to know the nature of the reaction. Since it is electronucleophilic substitution, it means that the alkyl halide is replaced by the hydroxide group from a nucleophile. Now, this is what we call the transition state, whereby we say that a transition state, the species present can form products or can go back to the reactants. Now, the reaction is SN2. This reaction is SN2. We call it SN2, or substitution nucleophilic bimolecular, simply because in the transition state, the entering hydroxide ion, all right, the entering hydroxide ion and the leaving halide, the entering hydroxide ion and the leaving halide are both partially bonded to the same carbon. Okay, both the entering hydroxide and the leaving halogen are both bonded to the same carbon. All right, so the variation, we're going to look at a graph that shows the variation of potential energy as the reactants are converted to products of this reaction involved. So let's look at the potential energy diagram. So when I'm drawing the potential energy diagram for the other reaction, I'm just going to draw so I will have the potential energy, write the whole word in kilojoules per mole. Then here I'm going to have the reaction path. So for this case, so we have alkyl halide Rx plus OH then here Of course, here we have the activation energy. Then at this point, we form our activated complex. So we call it our transition state. Then, of course, that is what we call the transition state. Then here we are forming our products. That is the alcohol, ROH, plus the iron. Then, of course, from here up to here, we shall call it our enthalpy of reaction, DH. This EA is the activation energy. So that is for the primary halide. Now, if I'm to explain this generally to you, at first, you see the potential energy is high. So more energy is needed to break the carbon halogen bond. Remember, I said that carbon is partially positive while the halogen is negatively charged, partially negatively charged. Now, this bond has to be broken. To break this bond, we need high amounts of energy. Remember, before the entering hydroxide comes, this bond must first be weakened. So to do so, a lot of energy is required. All right. And the energy required to break the bond is higher than the energy that is supplied by the formation of the new carbon-oxygen bond. Because at the end of it all, you end up forming COH. So you end up forming the carbon-oxygen bond of the system. So now, since at first more energy is required to break the carbon-halogen bond than is supplied by the formation of the new carbon-oxygen bond, and energy of the system increases, it has to increase until a certain point where the carbon-halogen bond is half broken, and all right, and the carbon-oxygen bond is also half formed, and that is the transition state. Okay. Now at transition state, the energy then decreases corresponding to the compression of the formation of the carbon-oxygen bond. All right, so that is what you need to know. At first, the energy is high because the energy needed to break the bond is greater than the energy supplied by the formation of the carbon-oxygen bond. But that energy increases until a point it reaches where the carbon-halogen bond is half broken and the carbon-oxygen bond is partially formed also. All right. So then it decreases until you completely form the carbon-oxygen bond, right? I think you need to know that the energy, the difference in this energy between the reactants in the transition state is what we call the activation energy. And it is that activation energy that reactants must possess to form the products. Now, the energy difference or the difference in energy reaction is 2. That is the bimolecular, because two molecules are taking part, rather the two molecules are taking part in the transition state. All right. Two species are taking place or are taking part in the transition state. Another thing that you should know that the molecularity of this reaction is 2, simply because the number of molecules or species involved in the transition state or the redetermining step is 2, whereby we have the OH and the alkyl halide. So I can say explain the energy level diagram, or I can say plot or draw the potential energy against reaction coordinate reaction pathway and explain it. So the explanation, maybe if I'm to write it, we need to know that first, more energy is needed to break the carbon halogen bond than is supplied by the formation of carbon-oxygen bond. So it has to increase, energy has to increase up to a certain point. When the carbon-hydrogen bond is half broken, you have to write all that, and the carbon-oxygen bond is half formed. It then reduces up to when the carbon-oxygen bond is completely formed. All right, so that is all about a primary alkyl halides. Then we've seen what we have noted from this. We've seen that it is molecularity 2, because 2 species are involved in the rate determining step. Remember, molecularity of the reaction is the number of molecules or species involved in the rate determining step, or in the transition state, or in the formation of the activated complex. So the molecularity is 2 because 2 species are involved. Remember, when we are starting this topic, I told you that molecularity is never 0, and it must be a whole number. You can't say that 0 reactants are involved in formation of these products, and you cannot say that a half a reactant has been involved. So it must be a whole number, and it must be never 0. So from there, let's look at the alkaline hydrolysis of tertiary alkyl halide. For alkyl halides, or what we call the tertiary alkyl halides. Now, when we are dealing with tertiary alkyl halide, I'm going to consider a point of 2-bromo, 2-methyl propane. It's what I'm going to consider, 2-bromo. Then 2-methyl propane, no space here, 2-bromo, 2-methyl propane, which is CH3, 3CBr. If you consider such a reaction, you need to know that for this one now, it depends only on the concentration of alkyl and is independent of the concentration of the hydroxide. So in this case, if you have CH3, then 3, then C, Br, plus sodium hydroxide, of course, aqueous sodium hydroxide, in presence of heat, we are going to form a tertiary alcohol, and then sodium bromide. Now, I've said that the rate of reaction of this is only dependent on the concentration of the alkyl halide. So it is K times the concentration of the alkyl halide. But is independent on the concentration of the hydroxide, so power 0. Implying that the rate of reaction is K, CH3, now you can see, you can already reduce the order and the molecularity. The molecularity is 1, right? Simply because the rate determining step, or the slowest step, has 1 molecule, as we shall see. All right, so during this is the first order reaction, simply because the rate is directly proportional to 1 of the reactants concentration, and that is the 2-bromo 2-methyl propane. Now, when you're carrying out a mechanism of this, because that is the one that is going to enable us to draw a diagram. So we have CH3, 3CBr. The bromine first goes off, and this is a slow step. Cleavage, or as this one is going off, we have to form a first intermediate, CH3, 3C, Br. Now, this BR that continues now to this is the first transition state. The moment you write a transition state, because you say that at this point, we must form products or reactants, so it will harmonize well and forms a carbocation, a tertiary carbocation. So C plus, then plus Br minus. Now, the second step will be this tertiary carbocation, CH3, 3C plus, here we shall have OH. This step here is very fast. So we have first step, but we shall form another intermediate, OH. But remember, I told you that after an intermediate, you have to form a product. So it is CH3, 3C, OH. Now this is another transition state. So that is the mechanism. The first step begins by formation of transition state, which results into the carbocation. Then from carbocation, we form a transition state that leads to the formation of alcohol. Now, the rate determining step is unimolecular breaking of carbon-hydrogen bond, and therefore we have to call it SN1. Okay, so this means that a nucleophilic hydroxide ion does not enter the reaction until the second or first step. It has to wait until the second, which is the fastest step. Now, this one is going to give us the variation of potential energy diagram, the variation of potential energy. This is the most amazing part. So here we shall have potential energy in kilojoules per mole. And here we shall have the reaction path. So the fact is that here you will have your reactants. So here you will form the first activated complex. Then here you will form another activated complex, which will now take you to the products. As simple as that. So here is where we have our CH3, 3, CBr plus OH. And at this point, that is where we have our first transition state, CH3, 3. This is where we have another transition state, which is CH3. Then is where we have our products, where we have CH3. Now, in labeling, of course, this is the transition state 1, right? Transition state 1 in full words. This one here is the transition state 2. Then of course, here we shall have our enthalpy of reaction. And from here up to here, we shall have our activation energy 2. And of course, from here up to here, we shall have our activation energy 1. As you put these unknown values, you have to define them. You have to tell me that EA1 stands for activation energy 1, EA2 stands for activation energy 2, whereas DH stands for the enthalpy of the reaction. Now, the molecularity of these this alkaline hydrolysis, tertiary alkanes, is 1, because in the rate determining step, you can really see one you can really see one species, which is the alkyl halide. All right. So it's one simply because the rate determining step, what we call the slowest step, has one molecule, which is the tertiary alkyl halide. Therefore, molecularity may often vary. Okay. Sometimes, okay, molecularity in most of the cases is the same as the order of reaction. And therefore, since molecularity can be the same as order of reaction, sometimes, so this is also first order. But still, we had already seen that during this reaction, the rate of reaction is dependent on only the concentration of the alkyl halide, but not the hydroxide. And therefore, we specifically look at the alkyl halide as the one involved in the rate determining step. Thus, molecularity is 1 and the rate of reaction is 1. All right. Now, in all their cases, the bond, the unstable complex, or the intermediate or the activated complex will always undergo bond reorganization, and by releasing some energy, a stable final product shall be formed. So that's all about those hydrolyses, and that is what you can need to know. Right. So here comes a question to all viewers for your own benefit. Here comes a question for all of us. And the question is, question 1. Two bromo 2 methyl propane reacts with aqueous sodium hydroxide to form two methyl propan-2-ol, Part A, write the equation for the reaction. B, draw an energy diagram for the reaction. C, state the Roman 1 rate determining step, and Roman 2 the technique which is used to study the reaction. Here, rate determining step for the reaction. Number 2, bromomethane reacts with aqueous sodium hydroxide, right? According to the following equation. The overall order is 2. Part A, draw a fully labeled diagram of energy versus reaction pathway. For the reaction. Explain your diagram. Let's say describe. Then B, explain what is meant by the term activated complex. All right. Then C, write Roman 1. Write equation for the reaction. 2, mechanism. Here you're going to outline the mechanism for the reaction. Can put an additional part that determine the molecularity for the reaction and give reason. Determine the molecularity for the reaction and give a reason. So this video introduced to us the potential energy level diagrams. In the last one, we are going to record experiment to determine the rate of reaction, or we can look at how to determine the order of reaction experimentally, and we call it a topic. Good time.